Hi everyone, this is a walkthrough of Pre-Calculus Notes 2.6, Limits and Slant Asymptotes. The notes are already filled out online, and so the purpose of this video is just to show the process. We start with a look at some patterns that come up in finding horizontal asymptotes. What we found last time was that if we tried to divide a numerator by a denominator of higher degree, we get no quotient, hence a horizontal asymptote of y equals 0. This is the first pattern that we fill in. Horizontal asymptote of y equals 0. If you'd like to take a moment to pause the video and make sure you can identify those, please give it a try. The first equation has a first degree over a second degree, so that will have an asymptote of y equals 0. The second is an expression of degree 0 over degree 2, so that's going to have an asymptote at y equals 0. The last one has a degree 3 over a degree 2 polynomial, and we'll see what to do with that later. Our second shortcut has to do with when the numerator and denominator have the same degree. We've been using long division to find this. For the first example, we need to look at what do we multiply 3x by in order to get 2x. This is fractional. 2/3 times 3 gives you 2. Continuing the long division, we get a remainder, which doesn't concern us. The quotient we have is y equals 2/3. In the second example, our quotient begins with 2, and the rest becomes the remainder. So our second horizontal asymptote is y equals 2. At this point, we stop to look at the pattern. Compare the original function to the horizontal asymptote. See if you can spot the pattern before we continue. The conjecture we came up with in class was that the lead coefficients determined the horizontal asymptote. 2x over 3x, that ratio is 2 to 3. The lead coefficients are 2 and 3. 4 and 2, 4 over 2 is 2. So we suspect that the last one is going to work out to a over b. Since it's a general case, this will prove that this pattern works. The question we need to ask is, what do we multiply by bx to get ax? Our suspicion that it's going to be a over b helps. We can see that if you multiply a over b by b, the b's cancel, leaving us with a. This leaves us with a constant, and so that is our remainder. So there we have it. If the numerator and denominator are the same degree, then the horizontal asymptote is going to be the lead coefficient over the lead coefficient. The next topic is very closely related to horizontal asymptotes. We're going to look at limits. The last time we looked at limits was in the first section of this chapter. We saw that on the right side, as x gets larger and larger, the limit would approach either infinity or negative infinity when we were dealing with these polynomials. Here we have a third option. On the right side, this graph does not go to infinity, does not go to negative infinity. It simply gets closer to the horizontal asymptote. If it approaches the horizontal asymptote, then the limit as x approaches infinity is 1. It will get closer to that horizontal asymptote as we go farther to the right on the graph. At this point, notice a subtle bit of notation. Originally, we looked at x approaching infinity. We will also introduce x approaching negative infinity. That is the whole left side of the graph. as x gets lower and lower. So, x approaching negative infinity talks about its left side end behavior. And as we can see, the graph is going to get closer and closer to that horizontal asymptote, with the limit being 1 again. So in short, as x approaches infinity or negative infinity, the limit is going to be the value of the horizontal asymptote. For example, in this first example, we know that this is going to have a horizontal asymptote of y equals 2 if we look at the lead coefficients. That means the limit will be 2 as x approaches infinity. Take a moment and try the next three, and I'll give you the answers. For example 2, the degree of the numerator is lower than the degree of the denominator. And so that's simply a y equals 0 horizontal asymptotes, making the limit 0. For number 3, we need to look at the lead term. That means we need to at least partially multiply this out. The lead term is 3x squared over 4x squared, meaning that these have the same degree, and so the horizontal asymptote is going to be at 3/4, and that is also the limit as x approaches infinity. The final one, we simply need to look at the lead terms again. In this case, we have negative 6x cubed over 6x cubed as the lead terms. Negative 6 over 6 is negative 1. So that's a horizontal asymptote and limit. Left side limit, if you note. Next, we're going to look at vertical asymptotes and how they relate to limits. Here's a graph with a vertical asymptote of x equals negative 3. Vertical asymptotes are interesting, and we can use limit notation to describe what happens on either side. So, on the left side of this asymptote, the graph is headed up toward positive infinity. On the right side, the graph is pointing down toward negative infinity. Notation-wise, we're going to look at x getting closer to negative 3, which is where the vertical asymptote is, and then we're going to look at what happens to the right and to the left. We have a superscript plus or a superscript minus to indicate the right side of the asymptote or the left side of the asymptote. On the right side of the asymptote, we're pointing down at negative infinity. That becomes our limit. On the left side of the asymptote, we're headed up. So we write positive infinity. Take a moment and look at these exercises based on the graph on the left. Notice that x could be approaching 3 or 0. That will tell you which vertical asymptote to look at. Numbers 5 and 6 are talking about the left and right side of x equals 3, that vertical asymptote. The left side descends, the right side ascends. Similarly, 7 and 8 look at the left and right side of x equals 0. On the left side, we descend. On the right side, we also descend. These are two different possibilities, and they make a good contrast. Finally, we step through slant asymptotes. You can fill in the text at the top, or you can step through, and you'll see that these arise naturally from the same method that we used to find horizontal asymptotes. First, we step through the usual process and figure out what we know. X can't be 1. It's not a whole because nothing canceled, so it's a vertical asymptote. The x-intercept, to find that, we set y equal to 0. We ignore the denominator because, as you recall, algebraically, our first move was to multiply through by the denominator. It would cancel and come to 0 on the right and left. So in this case, our x-intercept is 0. So we have 0, 0. For our y-intercept, we set x equal to 0. And we get 0 again. 0, 0. Now, this is the point where we would normally use long division to find the horizontal asymptote. Let's see what happens. the first thing to notice is that our quotient is not a constant. We have an x in it. Next, here's our constant term. There's our remainder. If we follow our usual rules, we put a y equals in front of this. We will continue to do that. Y equals x plus 1. That is going to be an asymptote. And when we graph it, it's going to look like this. Now we combine this with the vertical asymptote we found and the intercept we found, and we can see that we have a bit of a puzzle as to where to put the curve. Number line analysis can help. First, we need our critical points. We get those from the original function, 0 and 1. We do our usual workup on the number line, and this is what we get. Negative, negative, positive regions. Drawing these in, we have negative, negative, and positive regions. The second negative region is very thin, so I'm going to highlight it. The easiest way I know to fill in the curve is to focus on the vertical asymptote. If we look in the negative region that's highlighted, it's next to a vertical asymptote, and it's a negative region, and so it has to go down toward negative infinity. To the left of that, we have to stay negative. The number line told us so. In the region to the right of the asymptote, it has to be positive. That means we have to start at positive infinity. And we have to stay above the x-axis, and so we'll approach our horizontal asymptote. That is our long-term behavior. And so we have to go to that eventually. So this is one example of what a slant asymptote graph might look like. For another example, we look at number 2. The first thing we need to do is factor, and then we'll identify the domain. X cannot be negative 1. This ends up being a vertical asymptote because nothing canceled. And then we have our intercepts governed by the numerator, which are going to be 2. We have x could be 0, or x could be negative 3. For the y-intercept, I recommend using the polynomial form on the left. Plus 3 times 0, so we have 0 in the numerator, 0 plus 1 in the denominator. Y will be 0. So here are our 3 intercepts. When we find our slant asymptote or horizontal asymptote, notice we don't need to know ahead of time. It's just going to come out of our division. If we end up with a line that's horizontal, that's fine. If we end up with a line that's got a slope, that's fine. It'll be a slant asymptote. Our long division results in x plus 2, yielding an asymptote of y equals x plus 2. That has a slope of 1, and so that will be a slant asymptote. To wrap up, we go up and get our critical points so we can do number line analysis. As always, we get our critical points from the factored form. We have 0, negative 3, negative 1. We put these on a number line and find the positives and negatives. Filling out the chart, we get a sign pattern of negative, positive, negative, positive. We finish our number line chart and then go up to graph. First the asymptotes, then we fill in our intercepts, and then finally we look at the signs and fill in the curve. Our pattern was negative, positive, negative, and positive. Let me highlight the thin. Again, if we focus on the vertical asymptote, this is easiest to see. This positive region must head toward positive infinity. This thin negative region must be down toward negative infinity. Then, the negative region on the left will stay negative and approach the slant asymptote. The positive region on the right will stay positive and approach the horizontal asymptote. And we're done. Thanks for watching.